Hi everyone. In this video, we will finally discuss differentiability of scalar fields, providing a formal definition for what it means for a scalar field to be differentiable at a point in its domain. In previous videos, we've looked at both directional and partial derivatives. We've seen cases in which they both exist and don't exist, and we've also examined cases in which directional derivatives exist, but do not seem to have any relationship between the different directions. So in this video, in order to understand differentiability of scalar fields, let's first return to our definition of differentiability for a scalar function of a single variable. So recall that in Math 5610, we would have said that a function f, which mapped from, say, some open subset S of R into R, is differentiable at a point A in the domain S if this limit exists. So this is the limit definition of the derivative you would have seen back in a calculus course, right? And notice here, right, if I look at this, this actually looks like my definition of a directional derivative. So if you just sort of look at this definition, you feel like this just says that the directional derivatives ought to exist. And for a function from R to R, that really is true. But what we want to notice here is that there's another way to think about what this notion of differentiability means. We can formulate this in a different way, even for functions from R to R. And for functions from R to R, these two notions are equivalent to one another, whereas for functions from Rn to R, they are not necessarily equivalent. So notice we could take this normal limit definition and we could reformulate it into the following statement. We could say a function f is differentiable at A if there exists a scalar, which we'll call f prime of A, and a scalar function, capital E, which will depend on A and H, such that f of A plus H is equal to f of A plus f prime of A times H plus H times E of AH. And this should work for some H values that are sufficiently small, less than some delta. And the function E of AH should go to 0 as H goes to 0. So if we look at this expression to try and make sense of it, the first thing you might notice is that this looks sort of like a first-order Taylor approximation, right? Or just a linear, right? Another way we might say this is a linear approximation. If you ignore this last term here, right, this just says f of A plus H is equal to f of A plus f prime of A times H. This last term here is like an error term, right? This really represents the amount that your linear approximation is off from the true value of the function. And then what we specify here are just some properties of this error term, right? Namely, of course, H is going to 0. But if you take this whole error term and ignore the H, this piece is still going to 0 as H goes to 0. So to sort of see where this is coming from, right, you can sort of come back here and imagine, right, that f prime of A would be just defined as the limit as H goes to 0 of f of A plus H minus f of A all over H. Okay. And so if we sort of look at what's going on here, right? If I were to sort of plug that in here, right, then, sorry, instead of actually plugging that in here, let's do the following. Let's rearrange this expression here. So if I subtract f of A over and divide by H, this expression would become this. Okay. So if there exists this scalar, f prime of A, and this function which satisfies these properties, then if I take a limit of both sides as H goes to 0, right, I get that the limit as H goes to 0 of this it must exist, and this goes to 0. This is just a constant as far as h is concerned. So if this definition is satisfied, then f prime of a is in fact the derivative of this function. Okay. So what we want to see here is that this implies the differentiability. You can also, in fact, go the other way for functions from R to R. Okay. So these two really are equivalent definitions for functions from R to R. Now, for functions from Rn to Rm, these are not equivalent definitions. Okay. Again, as I mentioned, this is really something more like saying the directional derivatives exist. This is some other type of differentiability or other notion of differentiability, right, which is really here saying that your function is well approximated by a line, by a tangent line at the point A. So what we want to do is we want to try and generalize this notion to functions from Rn to R. Now, if I look at this definition here, the first thing I might want to do is start thinking about what sorts of things need to change. Well, the first thing I'm going to notice, right, is that here A is now going to be a vector, so H probably also needs to be a vector. Okay, so what I want to do here is I want to be adding on some small little vector quantity. So I'm going to have an A here, and I'll actually change this to V. So this will be A, and then A. This, again, will need to be something else. We have to think about what this needs to be. This will be a vector V. So now also, I can't just multiply two vectors together, at least not in the same way I can multiply scalars together. And then this will be, again, something about a vector V times this function here, which is some sort of scalar function. If I still want it to be a scalar function, it's going to need to be a scalar function of two vectors. And then whatever I multiply by here will need to be some sort of scalar quantity as well. So I've got to sort of figure out some things here. Now, what I really want to focus on here is what I really have here is a scalar times another scalar. Okay, and I have this scalar which is acting on the increment, right? The increment h that I'm moving away from A. So what I'm going to want here is not, I want to think about like, how do I generalize sort of scalar times a variable, right? So in one dimension, right, this is just like a function y of x, where it's just a scalar times some input. Well, when I move into higher dimensions, I typically think of those then, this is a linear function. I want to think of a linear transformation. And in fact, that's exactly how I'm going to do this. So let's look at our new definition of for differentiability of a scalar field and see how it relates here. All right, so if I want to think about a scalar field, F, which is going to map from some open subset of Rn into R, then I'll say that it is differentiable at a point A, but again, that A is now a vector in S, which is a subset of Rn. If there exists now I don't have a scalar, I have a linear transformation, which I'm going to call T sub A. So this linear transformation, just as F prime of A depended on A, this linear transformation depends on the point you're taking the derivative at. And you'll notice down here now what I'm doing is I'm applying that linear transformation to the increment vector V. Okay, so what I want to be satisfied here is I want f of a plus v. So v is just another vector in Rn, okay, with sort of sufficiently small magnitude, right? Because I only needed to hold for vectors of sufficiently small magnitude because I'm going to take a limit as the norm of v goes to 0. So I have a plus v is equal to f of a plus this linear transformation T sub A applied to V. This is the equivalent of f prime of A times H. So this linear transformation T sub A is like f prime of A times V. But now this isn't multiplication, this is a linear transformation, T of A being applied to the vector V. Just as f prime of a times h when we were in like just the real, just r, right? That was really the linear transformation f prime of a times x applied to h, setting x equal to h, right? And then here we're going to add, okay, again, here we have e of AV. So this is just like the e of AH from before. And then we're going to multiply by the norm of V. Okay, so that's going to take the place of the H before. So really in this previous definition, H was really sort of pulling double duty here in some sense, namely that it was both here acting as sort of something that just gave us magnitude, and here acting as something that gives us both magnitude and direction. And in the case of R, it's fine that this isn't strictly speaking a magnitude. We can deal with that. But as we move into higher dimensions, we do need to be careful to make sure that this is in fact a magnitude. Okay, so our definition of differentiability is a scalar field is differentiable at a point A if there exists this linear transformation and this scalar function, where this scalar function needs to satisfy the same property. E of AV needs to go to 0 as V goes to 0. Okay. So this needs to go to 0. Okay. And if that is the case, that there exists this linear transformation and this scalar function that satisfy these properties, then we will say that our scalar field is differentiable at A. Now, again, you could rearrange this and sort of get something that is equivalent-ish to the limit definition of the derivative we've seen before, but again, slightly different because you have this linear transformation. Now, what is this linear transformation like? Why is that a big deal? Well, one of the things we saw in previous examples is you could have directional derivatives, right? But there was not a linear relationship between those directional derivatives. In some ways, what this is enforcing is not just that the directional derivatives exist, but that they form a linear subspace. So, for example, if you have some function here, let's just sketch some function and some sort of function, right? Some surface here that's giving us a scalar function. What this is saying is that at this point, so I have some point A in the domain. I want to understand if we're differentiable at that point. It's saying that here, not just that the directional derivatives should exist, but that they should form this sort of linear subspace that gives us like a tangent plane at that point. Okay. So differentiability has to mean more than just the directional derivatives existing. It has to mean that they form a linear subspace so that we can really approximate this function well, right? We can approximate a point near, we can approximate f of a point near A, so A plus V. I can approximate that point by just taking f of A and then applying this linear transformation T sub A to the difference V. And then whatever the error is, these conditions basically say, but the error, there'll be a little bit of error, but it ought to be small. Okay. So that's what differentiability ought to mean here. So the big difference is that here for functions, for scalar fields, our definition of differentiability is really that the function is well approximated by some sort of tangent plane. Now, of course, whether that's a plane or a hyperplane or something, I mean, geometrically, what exactly that object is we don't really care about what the object is geometrically, just that it forms this linear, it has this linearity property here, right? And this error property here that will ensure that our scalar field is differentiable. But again, the way to think of it is sort of, it's well approximated by some sort of linear thing. All right, so the whole point of some of this was we really wanted differentiability to imply continuity, right? So we saw in the previous video that we couldn't sort of have our notion of differentiability just be that all the directional derivatives exist and expect continuity to follow from that. So what we've done is we've changed our definition of differentiability to this notion of it's well approximated at the point by some linear thing. And what we would like to do is show then that under that definition of differentiability, my function, if it is differentiable at a point, must be also continuous at that point. Okay. It actually turns out the proof here is actually quite simple. So let f from S, which is a subset of Rn into R, be differentiable at some point A in the domain. Okay, well, what does that mean? Then this is just the definition. There exists a linear transformation T sub A, which maps from Rn into R, and a scalar function E of a V such that f of A plus V equals f of A plus T sub A of V plus norm of V times E AV with EAV going to 0 as V goes to 0. All right, so now let's just take a limit of each side as V goes to 0. So notice that as V goes to 0, that's really like saying this input here is going to A. Okay, so then the limit, I look at the limit as x approaches A of f of x. That's really the same as saying the limit as V goes to 0 of f of A plus V. Right? As x goes to A, that's the same as V going to 0 here. And now if I look at this expression, so this will be the same as the limit as V goes to 0. And should be careful, these are 0 vectors, right? This is a limit in Rn. So this would be the limit as V goes to 0 of f of A plus T sub A of V plus norm of V times E of A V. Now, if we look at what happens to each of these terms as V goes to 0, this is linear, so this is continuous, and any linear operator applied to the 0 vector is just 0. So that just goes to 0. This is going to 0, and certainly this is going to 0 by our assumption about this error term here. And this piece is also going to 0. The norm is continuous. So all those things go to 0 and in the limit, and what I'm left with then is that this is just equal to f of A. And so what I have here is that the limit as x approaches A of f of x is just equal to f of A, and hence f is continuous at x is equal to A. So again, the nice thing here is that this notion of differentiability actually gives us exactly the theorem that we were sort of worried about which is it gives us that a function which is differentiable at a point must be continuous. So in some ways, this is, I mean, there's never right or wrong definitions in math necessarily. Definitions just are, and then we look at consequences of those definitions. But certainly, this definition gives us some very desirable properties, right? So this definition of differentiability gives us the property that a function that is differentiable at a point is also continuous at that point. And again, that doesn't make it the right definition, but it certainly makes it a very good one. So now that we have a notion of differentiability, right, we might want to start thinking about, okay, how do I calculate these things, right? So in order to do that, though, let's first, we don't really, this definition formally is a little difficult to work with. We'd like a little better way of understanding, like, what is this T sub A, right? What is this linear transformation that's supposed to be like the derivative? We actually call that transformation the total derivative, but we want to understand, like, what is it made up of? It should have something to do with the directional derivatives, right? Or the partial derivatives, right? So we want to understand a little better what exactly that connection is. So in order to understand that, we want to sort of prove the following theorem. And this looks like a lot, and we'll actually see that some of it is just a consequence of previous parts. So let's assume f is differentiable at a. Then we want to show the following three things. The first is we want to show that if our function is differentiable, then all the directional derivatives exist, and the derivative of f at a with respect to y is equal to this linear transformation applied to y. Okay. Now, I've written here for norm of y equals 1, and let me explain that. So for directional derivatives, right, we're always assuming the norm of y is equal to 1, which is why I've written this, right? Because for a directional derivative, this should be this. But actually, if you just wanted the derivative of f at a with respect to y, not a directional derivative, so y has any magnitude, it's still actually equal to this. So this holds not just for norm of y equals 1, but since we're thinking about directional derivatives in this case, I just wrote that for norm of y equal to 1. All the partial derivatives exist, okay? Now, in fact, this follows from this, right? Because partial derivatives are just directional derivatives in the direction of the standard basis vectors, right? So the kth partial derivative is just the derivative of f at a with respect to the kth standard basis vector. So we actually, this isn't a separate thing we need to prove. This follows immediately from 1. Now, this last piece actually gives us sort of a way of calculating the derivative, the total derivative of the function f at a evaluated at v, right? So like if I want to understand what this linear transformation does to a vector v, what this tells me is, well, basically just take the components of v, multiply them by their respective partial derivatives. So you take the kth component of v, you multiply it by the kth partial derivative of f at a, and then you take all those products and add them all together. Okay. So again, we'll see how all of that falls out as we go through this theorem. Now, again, what this gives us is a relationship between directional derivatives and partial derivatives, because they're just a special kind of directional derivative, and the total derivative. And it also gives us a formula for evaluating the total derivative at a particular point. All right. So let's take some time to walk through this theorem and understand it. Okay. So let's start with 1. Okay. So here I just want to prove that the derivative of f at a with respect to y is equal to t sub a evaluated at y. All right. Well, in order to do that, let's sort of get a trivial case out of the way first. Okay. So note that if y is equal to the 0 vector, okay, so if y is equal to the 0 vector, then, okay, well, T sub A, well, evaluated at Y, that's just going to be T sub A evaluated at the zero vector. This is, again, we're assuming F is differentiable, so this is, in fact, a linear transformation. Any linear transformation applied to the zero vector is just zero. Okay. So that's just equal to zero. And if we look at F prime of A with respect to Y, that would just be the limit as H goes to zero of, what's this going to be? It's going to be F of A plus HY, but Y is a zero vector. So it's just going to be F of A minus F of A over H. Well, that's always going to be zero. This is also just going to be zero. Okay. So T sub A of Y is equal to F prime of A with respect to Y. Trivially, if Y is the zero vector. Okay. Now, we basically want to get that case out of the way so we can deal with the more interesting case. Okay. All right. So now let's assume, sort of switch to a different color here. So now assume Y is not equal to zero. Perfect. Okay. So since F is differentiable, at A, then we have F of A plus V is equal to F of A plus T sub A of V plus norm of V times E of AV. Again, where this term goes to zero as V goes to zero. And this is, again, a linear operator, okay, or a linear transformation. Okay. So now I'm going to let V, well, so sorry, let me emphasize here too. This holds, let me just write this out. For all V with right, I need that limit. I need to be able to take a limit as V goes to zero, which means I need this to be defined for all V in some neighborhood around the origin. In order to take that limit, I need this to be defined on some neighborhood of the origin. So let R be some radius so that this is defined, that this equation holds for all V within some neighborhood of the origin. Okay. So since that works, we can take and set V equal to H times Y, where I don't want H to be zero, right? Because if H was zero, this would be the zero vector, and I'm sort of trying to avoid the zero case. Okay. And I should also make sure that this H times Y gets me within that R, so I want H times the normal Y to be less than R. Again, so basically make sure the norm of this V will be less than R. Okay. Well, since my T sub A, this is a linear transformation, then we have that T sub A of HY, which is just T sub A of V, is equal to H times T sub A of Y. And so if I start plugging back in here, what I would get is F of A plus HY equals F of A plus H times, so I'm plugging in for V, HY, T sub A of HY is equal to H of T sub A Y. Plus, now I'm going to plug in HY here. That's going to give me an absolute value of H times norm of Y. E of A V. Okay. Now I'm going to leave this as V because it's actually not important that I switch this one around here. Okay. Now I'm going to do a little bit of algebra here. I'm going to subtract this over. I'm going to divide everything through by H. So this gives me that F of A plus HY minus F of A all divided by H is equal to, okay, so I subtracted this over, and I'm dividing both sides by H. Here I have an H that's going to go away, so this is going to give me a T sub A of Y plus, this is going to give me what, an absolute value of H, norm of Y divided by H times E of A V. Okay. Now I want to look at both sides and essentially say, okay, what's happening here as I let H go to 0? Okay, so as H goes to 0, if I take a limit of both sides now as H goes to 0, over here I'm just going to write this. Now over here, if I take a limit as H goes to 0, what's going to happen? Well, this doesn't depend on H. So this is just T sub A of Y. Okay. Now, if I look at this over here, okay, this term, right, it's either going to go to positive or negative 1, right? So as H goes to 0, right, this is either going to go to positive or negative 1, depending on which side it's approaching 0 from. Most importantly, I don't even care what it's bounded, okay? So as long as this is bounded, I'm fine. So this is bounded. This is bounded, right? Y is just some vector, okay? And this term, well, as H goes to 0, HY is going to go to 0, so V is going to 0. And as V goes to 0, this term goes to 0. So in the limit, as H goes to 0, this just becomes this quantity. And over here, this whole term disappears and goes to 0. So you're just left with a T sub A of Y. So now, but if I look this side, this is just the definition of the derivative of F at A with respect to Y. And in the limit, this becomes T sub A of Y. Okay. And so what we have shown here is that if our function is differentiable, if it is differentiable, okay, then the total derivative of the function at A evaluated or acting on Y is just the derivative of F at A with respect to Y. Okay, so really what it says is if your function is differentiable, then that term that is T sub A of V, it's really just the derivative of F at A with respect to V. So if it's differentiable, then that total derivative thing really just encapsulates the information about all of the directional derivatives. Okay, that's what that total derivative encapsulates if your function is differentiable. All right. Now, again, as I mentioned, the second part, we actually don't need to prove anything. The second part, I could essentially rewrite the proof by just saying here that Y must be the vector EK, right? And then when I go through, I'd eventually end up here with just, this would be the definition of the partial derivative or the kth partial derivative of F. So again, once we prove this for directional derivatives, it's also true for partial derivatives because partial derivatives are just a special kind of directional derivative. All right. Now, the thing that remains to be proven is that formula that sort of tells us how we can calculate the total derivative acting on some vector by using a sum of products. So let's take a look at that. All right. So now skipping to 3. Here we're going to make use of the linearity of that total derivative. Okay. So if, say, we have a vector v, which is made up of components v1, v2, all the way up to vn, okay, then I can write v as the sum, k equals 1 up to n, of vk times these vectors ek, where again, ek, right, is just the kth standard basis vector, right? So just in the kth position, I have a 1. Everywhere else, I have zeros, right? So this is basically saying I can take this vector and rewrite it as v1 times 1, 0, 0, 0, 0, 0, 0, plus v2 times 0, 1, 0, 0, 0, 0, 0, so on and so on and so on. So this is the decomposition of the vector v into the standard basis. Now, if I do that, okay, then I can say, if I look at t sub a of v, okay, well, that's going to be what? T sub a of this thing. And now this is linear, which means what? I can break it up over sums and I can pull out scalars. So I can rewrite this as the sum k equals 1 to n. So I can apply TA to each of these terms, but then these vk's are just scalars that I can pull out. So I get this. But now what did I previously show? In part 1, right, I showed that T sub A of y is just equal to f prime of A with respect to y. So what should T sub A of this vector EK be? Well, it ought to just be f prime of A with respect to EK, but this is exactly what we defined to be the kth partial derivative of f at A. So this term here then just becomes the kth partial derivative of f at A, giving us the formula that we desired. All right. Now, this is great. This is the theorem we wanted to prove. But I want to notice that when I look at this, this almost looks like an inner product of things, right? This looks like, right, I have a sum of products of scalars. So this sort of looks to me like an inner product of the vector v with an inner product of the vector whose entries are the partial derivatives with respect to each variable. So I could write this almost as v dot product with whatever this is, okay? Now, it turns out, and you may have remembered this from Calc 3, this is a vector that we use quite a lot. We call it the gradient of f at A. Okay. So what we want to do then is actually explore this gradient vector a bit more to understand. Obviously, it has some help, it is of some help here, but we want to understand, like, what other things might this gradient vector, is it only useful here? Right? Is it only useful for calculating the total derivative applied to some vector, or does it have other uses? And you may remember, from Calc 3 that, in fact, this has quite a lot of uses. We just want to make sure we remember what some of those are, improve some of those properties that you would have used about the gradient vector. All right. So first, let's just formally define this, right? So let F map from S into R be a scalar field. And let's imagine that all the partial derivatives exist at some point A. Then the gradient of F at A is the vector. So we write it in two different ways. We can write gradient of F at A using this upside down, sometimes called a nabla. Nabla F of A, or we can write it as, sometimes you'll just see it written as grad F of A. Both of these just mean the same thing. They mean the gradient. I'll tend to use this definition or this notation more. But by definition, it's just you take the partial derivative of F with respect to the first variable evaluated at A, take the partial derivative of F with respect to the second variable evaluated at A, so on and so on and so on. So just as a quick example and reminder, let F of xy equal, say, xy squared. Let's find the gradient of F at the point 1, 2. Okay. So to form the gradient vector, the gradient of, the gradient of F, just at an arbitrary point xy. So the first entry here is just going to be partial derivative of F with respect to x. Second entry will be partial derivative of F with respect to y. So partial derivative of F with respect to x, I pretend y is constant. So then I've just got constant times x, so that's just y squared. Partial derivative with respect to y, I pretend x is constant. So I have constant times y squared. That gives me a 2xy. Okay. And now if I want the gradient of F, at the point 1, 2, and then I simply plug in 2 for y, so that'll be 4, and 4. Okay. 2 times 1 times 2. All right. So that gives me this gradient vector. Now let me make a couple of remarks. Note that the gradient is not a unit vector, right? So just always be aware of that, right? It is not a unit vector necessarily. It could be, but often it is not. Okay. The other thing we want to note is that it came up in that formula before that the gradient vector has something to do with the total derivative, but remember that the hypothesis of that whole theorem was that you already knew the function was differentiable. We can define the gradient as long as all of the partial derivatives exist. But just because all of the partial derivatives exist does not mean the function is differentiable. So that equation from before, right, that I had basically written down where t sub a of v is equal to the gradient of f at a dotted with v, this only works if you already know your function is differentiable. Okay, if you're already differentiable, then you know that all of your partial derivatives exist, so the gradient exists. But if you know that all of your partial derivatives exist, then your gradient will exist, but that does not necessarily mean that your function is differentiable. Okay, so again, you have to be very careful here about what all of these different differential type objects, like what they mean when they exist, and whether or not a particular type of differential object existing is enough to claim that the function is differentiable. Again, unless the differential object you're talking about is the total derivative, then existence of any other differential object is usually not enough to conclude differentiability. All right, so other than being useful for that formula, though, we might wonder, like, what is the gradient good for? So again, we've already seen this one part. So if f is differentiable at a, then any directional derivative can just be thought of as an inner product of the gradient evaluated at that point, inner product with that vector. Okay, so again, you have to know f is differentiable, right? But if you know f is differentiable, then we can always use this formula for calculating directional derivatives. Now, this is where when you're teaching a Calc 3 course, sometimes you have to be careful because students will begin to think that this is the definition of a directional derivative. Okay. This is not the definition of the directional derivative, right? The directional derivative is defined using that limit definition. It is a formula for calculating a directional derivative when you know that your function is differentiable at that point. Now, again, in a Calc 3 course, many times the examples you're giving them to do this, it is differentiable at that point. But you want to be a little careful to emphasize that this isn't the definition. This is just a formula that we can use when f is differentiable, which again, in a Calc 3 course, probably most of the time, the functions they're going to be dealing with are differentiable. But again, for us in Math 5620, we need to know this is a formula which is only valid when the function is differentiable. If your function is not differentiable, but let's say all the partial derivatives exist, you have to be careful because you can compute this. It just won't be equal to the directional derivative. Okay. All right. The other thing that the gradient often gets used for, and actually is used quite a lot in application, is that the gradient always points in the direction of the maximum value of the directional derivative. So this theorem, if we read this here, so let f be differentiable at a, and assume that you're at a point where the gradient is not the zero vector. Okay, so it's not the zero vector, it's pointing in some direction. Then the maximum value of the derivative of f at a with respect to u, so over all directions u that you might take the derivative in, the maximum value of this derivative is equal to the norm of the gradient, and it's achieved when u points in the direction of the gradient. So what this is saying is that the gradient vector points in the direction of steepest descent. So if I were to draw a picture over here, so I have some function, it's given by some sort of surface, looks like this. Okay, again, you're starting to notice I have limited ability to draw a lot of three-dimensional surfaces. So you pick some point in the domain, some fixed point A, okay, and you go up here to the surface, okay, and you can imagine you're standing on this surface. So here you are standing on the surface, right? And you're wondering, of all the directions I could go, which direction is going to be the steepest? And what this theorem tells you is if your function is differentiable at that point, the direction you want to move, so again, the gradient is going to be a vector in the domain space, okay? So it's the direction you want to move is actually the gradient of your function f at this point A, and it's going to take you up. So imagine you sort of map this up here to the surface. It's going to take you in the steepest uphill direction from that particular point, okay? If you want to move downhill as quickly as possible, then the minimum value of your directional derivative is minus the norm of the gradient, and it's achieved when u points in the opposite direction of the gradient. So if you want to go, I mean, it sort of makes sense, right? Like if I find a direction in this direction, I'm moving uphill the quickest, and I want to go downhill the quickest, I ought to just turn directly 180 degrees around, right? And that's exactly what this says, right? You just go back in the opposite direction. That'll take you down as quickly as possible. And then this last piece says, if you want your directional derivative to be 0, then you just move perpendicular to either of these vectors. So if I want to, in either of these directions, I'd be perpendicular to the gradient. And if I came up here, these would be moving along what we call a level set, right? So you wouldn't be changing height at all here, right? You'd just be walking sort of around a curve, right? That doesn't change height. All right. Now, in application, this actually has tons of uses. One of the ways of computationally finding maximum and minimum values of multivariable functions and other types of functions, as a matter of fact, is called like gradient descent or steepest descent. So one of the ideas you can sort of imagine you wanted to computationally find the minimum of this function. Now you can see this function has a local minimum here, and let's say a global minimum down here. And the idea is you basically pick some point where you think the minimum value might occur. Just guess. It's better if you guess close to the actual point, but let's say you don't. So maybe you pick some point over here. So you go up to your surface and you say, okay, that's probably wrong. So let me calculate my gradient at this point and let me move a little bit in the direction of that gradient, or sorry, negative that gradient. The negative that gradient is going to take me the steepest downhill. So then it gives me, I do that, and I'm actually moving in the domain. So I move maybe over here. Negative my gradient takes me over here. Okay, then I look at this point and I calculate a gradient here, right? And so it tells me maybe move a little bit over here. And so I move over here, and that maps up to the surface at this point over here. And I keep doing this and following it along until eventually, right, maybe it leads me, right, maybe in the next step, my gradient sort of takes me down here and gets me to the local minimum. Now, once I'm at a local minimum, and this is something we'll want to show later, my gradient vector is going to be 0 if I'm differentiable. So then eventually this sort of process can end. But so this notion that the gradient points in the direction of steepest ascent, negative the gradient points in the direction of steepest descent, can be very useful computationally in many algorithms. So if you ever study like numerical optimization, this is something that comes up quite frequently as a method of solving these sorts of problems. So this is, oh, sorry, and I should mention, actually, all of these proofs, if you wanted to prove these things, these all really come out of the fact that if you want to calculate f prime of a in the direction of u, since we're differentiable, we can just use our formula that this should be gradient of f at a inner product with u. And one fact you can use about inner products is that this is equal to the norm of the gradient of f at a times the norm of the gradient, times the norm of u times cosine of theta, where this theta is the angle between these two vectors. Okay, so you ask yourself, okay, u is fixed. The gradient at this point is a fixed vector. So, sorry, u is not fixed, but it has a fixed, it's a unit vector, so it has fixed norm. So this norm is just 1. This is really gradient of f at a times cosine of theta. So this is fixed. U's magnitude is fixed, but its direction is not. So how would I maximize this thing? Well, to make this thing as large as possible, I should make cosine as large as possible. So the largest cosine can be is what? It's 1, right? And when is cosine equal to 1? Well, that's when theta is equal to 0. That means the angle between u and the gradient of f is 0. That means they're pointing in the same direction. So the maximum value of this occurs when theta is equal to 0, which means that u points in the direction of the gradient of u. And then that just gives you 1, and so this derivative value is this. If you want to minimize this, the smallest this could be is -1. That happens when theta is equal to pi, right? So these would point in opposite directions. So you want u and the gradient of f to point in opposite directions. When is this equal to 0? Well, it's equal to 0 when cosine is equal to pi over 2. That means that u and the gradient of f are perpendicular to one another. So all of these results fall out of just analyzing this equation to understand when these things are maximized and minimized. All right. Now, this really concludes, although we will say a little bit more later on about the gradient, which can be useful for a number of things. This really concludes our discussion of differentiability of scalar fields. So in the following videos, what we'll want to do is think about differentiability of vector fields. And in fact, what we're going to see is that quite a lot of what we learned about differentiability for scalar fields can actually carry over to differentiability of vector fields. We'll just think of the vector field sort of component by component and apply our results from differentiability of scalar fields.